I am Dr. V. Janaki, Assistant Professor, PG and Research Department of Chemistry, Sharada College for Women, Salem 16. In this content, let us see what is meant by the common ion effect and what is meant buffer solution and then mechanism of buffer and how we can calculate the pH of a buffer and what are all the acid-base indicators and then theories behind the acid-base indicator and what are all the choice of indicators for different types of titrations. So first let us see what is meant by the common ion effect. Common ion effect is nothing but the suppression of the dissociation of a weak acid or a weak base on the addition of its own ions is called the common ion effect. If a salt of weak acid is added to a solution of weak acid itself, the dissociation of the acid gets decreased. For example, the addition of sodium acetate to a solution of acetic acid, it suppresses the dissociation of one acetic acid because it supplies more acetate ions. So automatically it suppresses the dissociation of acetic acid. Similarly, if we add HCl also, it supplies more number of H plus ions. It also pushes the equilibrium to the left and it also suppresses the dissociation of acetic acid. Similarly, if the dissociation of the weak base, for example, ammonium hydroxide is also suppressed on the addition of ammonium chloride, it supplies more number of ammonium ions. Similarly, the addition of a strong base, for example, sodium hydroxide, it also supplies more number of OH minus ion. So here it also pushes the equilibrium to the left and it also suppresses the dissociation of ammonium hydroxide. Now let us see what is meant by buffer solution. For many purposes in chemistry, it is necessary to have a solution whose pH does not change much even after the addition of small amount of strong acids or alkalis. Such solutions are called buffer solution. A buffer solution is a one which can resist change in its pH on the addition of small amount of acid or a base. So we consider a solution of sodium chloride in water. We know that its pH is 7. By the addition of even 1 ml of 1 molar HCl solution to 1 liter of sodium chloride solution, it lowers the pH of the solution from 7 to 3. Similarly, if the addition of 1 ml of 1 molar sodium hydroxide solution to 1 liter of sodium chloride solution, it raises the pH of the solution from 7 to 3. Therefore, the sodium chloride solution is not a buffer. Here, the example for the buffer solution is ammonium acetate. The pH of the ammonium acetate is also 7. By the addition of same amount of acid or alkali, it does not causes any appreciable changes in its pH. Thus, ammonium acetate is a buffer as it can resist the alteration in its pH on the addition of an acid or a base. Now, let us see what are all the types of buffer solution. The first one is a weak acid together with a salt of same acid with a strong base. These are called acid buffers. Here, the combinations are acetic acid plus sodium acetate. And the second one is a weak base and its salt with a strong acid. These are called basic buffers. Example, ammonium hydroxide and ammonium chloride. Now, let us illustrate the mechanism of buffer action by taking the examples of a common buffer system consisting of a mixture of solution containing acetic acid and sodium acetate. Here, the pH of the buffer is governed and its equilibrium is given as CH3COOH dissociated into CH3COO minus plus H plus. Here the buffer has large excess of acetate ions which is produced by the complete ionization of sodium acetate. That is CH3COO Na gives Na plus plus CH3COO minus. Now let us illustrate what happens by the addition of acid. Upon addition of HCl, the increase of H plus ions concentration, then it combines with the acetate ions to form undissociated acetic acid. We know that acetic acid is feebly dissociated. Thus, the pH of the buffer solution remains constant. However, due to the increased concentration of acetic acid, the equilibrium will be shifted slightly to the right. Increase in the concentration of H plus ion. This shows that there will be a slight increase of pH of buffer solutions. Now, by the addition of sodium hydroxide, when sodium hydroxide is added to the buffer solution, the OH minus ion then combines with the H plus ion of the buffer to form water molecules, and therefore the pH of the original solution is restored. However, due to the increase in concentration of acetic acid, the concentration of H plus ion is slightly less, and therefore the pH is slightly higher than the original pH of the buffer solutions. Now let us see the mechanism of basic buffers. Here the basic buffer is a mixture of ammonium hydroxide and ammonium chloride. Upon addition of HCl, the H plus ion combines with the OH minus ion of the buffer to form water molecules. Therefore, the equilibrium will be shifted to the right because the addition of H plus ions are neutralized and therefore the original buffer is maintained. When sodium hydroxide is added to the buffer solution, here the OH minus ion will combine with the excess of ammonium ions to form feebly dissociated ammonium hydroxide. Here also the pH of the buffer is maintained constant. Now let us see the calculation of a pH of a buffer solution. Now let us consider a general expression, that is Ha. It is a weak acid. The weak acid will be dissociated into H plus plus A minus. According to the law of mass action, the Ka, that is equilibrium Ka, is equal to the concentration of the product divided by the concentration of the reactant. Therefore, Ka is equal to the concentration of H plus into concentration of A minus divided by the concentration of the reactant, that is Ha. Here we are bringing this H plus the left side. So H plus is equal to Ka into concentration of Ha divided by concentration of A minus, where the concentration of the acid is the initial concentration of the added acid and the concentration of the salt is that of a salt used. So here we are taking the negative logarithms of both the sides of the above equation. We have minus log of H plus is equal to minus log of Ka minus log of concentration of the acid divided by the concentration of the salt. We know that minus log of H plus is equal to pH and log Ka is equal to pKa. We are substituting the minus log H plus values and log Ka values in the above equation. Therefore, the equation becomes pH is equal to pKa minus log of acid divided by the salt. And then we can rewrite the equation pH is equal to pKa plus log of salt divided by the acid. And therefore the equation becomes pH is equal to pKa plus log to the concentration of salt divided by the concentration of the acid. The above equation is known as the Henderson equations. Here we can calculate it for the basic buffer also. Here we will get the equation as POH is equal to pKb plus log of salt divided by the base. Now let us see what is meant by acid-base indicators. An hydrogen ion or acid-base indicator is a substance which changes its color within the limits with the variation in pH of the solution to which it is added. The pH range over which the color change occurs varies considerably from one indicator to the another indicator. For example, the methyl orange gives full acid color, that is red, when added to a solution whose pH is 3 or below, and the full basic color, that is yellow, in a solution whose pH is 4.4 or above. Here, the pH range of the methyl orange lies between 3 to 4.4. Here, the next one is the phenolphthalein. The phenolphthalein is another common indicator which gives the acid color, that is a colorless, in a solution of pH 8.3 or less, and full basic color, that is a pink, in a solution of pH 10 or above. Thus, phenolphthalein can be used to determine the pH range, especially between 8.3 to 10. Now, let us see the theories behind the acid-base indicators. The first one is Oswald theory. According to this theory, the hydrogen ion indicator is either a weak acid or a weak base. Let us consider here it may be an acid having a formula of HIN. Here it's dissociated into HIN dissociated into H plus IN minus. According to this theory, the undissociated HIN has one color, while the ion IN minus has another color. According to the law of mass action, the equilibrium constant, that is Kin, for the above equation is written as Kin is equal to the concentration of the product, that is H plus into In minus divided by the concentration of HIN. Here Kin is known as indicator constant. Now let us explain the theory of acid indicators by taking the examples as phenolphthalein. Phenolphthalein is a colorless weak acid. It dissolves in water and dissociated into give colorless hydrogen ions and the pink colored anions. And here it is represented by the equation HPH dissociated into H plus pH minus. Here the phenolphthalein or any other indicator first undergoes a reversible tautomeric change into a substance of a different color, which then gets dissociated completely to give colored cations or maybe an anions. Here for the phenolphthalein it is represented here, that is HPH colorless, changes into the colored tautomeric form, and then it gets dissociated into H plus colorless and then pH minus pink. Now if the solution is acidic, the hydrogen ion furnished by the acid suppress the dissociation of phenolphthalein. Therefore, the equilibrium will be shifted towards the left. That is a common ion effect, and therefore the solution remains colorless. Suppose in the presence of alkali, there will be an increased hydroxyl ions, and these hydroxyl ions combine with the H plus ion by the indicator to form undissociated water, and therefore the equilibrium will be shifted towards the right, giving more number of colored anions, that is a pink color. Therefore the solution appears pink. Thus the indicator will be a colorless in an acid and pink in the alkaline solution. Now let us see the action of methyl orange. Methyl orange is a weak base and it is represented as MEOH. It dissolves in water and undergoes dissociation to a small extent. Here the undissociated molecules are yellow while the cations Me plus are red in color. And it is the dissociation is represented as MEOH dissociated into Me plus OH minus. Here the Me plus is red color whereas OH minus is colorless. Suppose if a solution is acidic, the hydrogen ion combine with the OH ions that is produced from the indicator to form the undissociated water. Here this shifts the equilibrium to the right, giving more number of red colored, that is Me plus ions. Therefore, in acidic solution, the indicator gives red color. Whereas in the presence of alkali, the OH minus ion suppresses the dissociation of methyl orange. Here, therefore, the solution in the alkaline medium remains yellow in color. So far, we have seen what is meant by acid-base indicators and what are all the theories behind the indicators. Now let us see the choice of suitable indicators. The choice of suitable indicator for a particular acid-base titrations here depends on the nature of the acids and bases involved in the titration. And these are the different types of titrations, that is a strong acid with a strong base, weak acid with a strong base, a strong acid with a weak base, and weak acid with a weak base. Now let us see the titration of a strong acid with a strong base. Here we can see the titration curve when sodium hydroxide is added gradually to the strong acid, that is HCl. We can see from the curve that the pH of the titrations rises extremely slowly in the beginning. In the vicinity of the equivalence point, the pH rises dramatically and almost the curves become vertical. Beyond this, the curve becomes almost flat. That shows a slight rise of pH when only excess of base is also present in the titration. Here the vertical portion of the curve will be extends from pH 3 to pH 7. Here the pH range of methyl orange, we have already seen that it is between 3.1 to 4.4. And then the phenolphthalein is 8.3 to 10. And therefore they fairly narrow and falls on the vertical curve. And therefore both the indicators, that is methyl orange and the phenolphthalein, are a suitable indicators for titrating of strong acid like HCl with a strong base like sodium hydroxide. The next one is titrating a weak acid with a strong base. Here we can see the curve, titration curve when sodium hydroxide, which is a strong base, is added to an acetic acid, which is a weak acid. Here the pH curve rises slowly in the beginning, but near the equilibrium point, the pH changes abruptly from 6 to 11 and the curve becomes vertical. Phenolphthalein, it has a pH range of 8.3 to 10. that falls on the vertical point of a titration curve. Here, the pH range of a methyl orange is 3.1 to 4.4, yet it does not fall on the vertical curve. And therefore, for titrating of weak acid, that is acetic acid, and with a strong base like sodium hydroxide, the phenolphthalein is only a suitable indicator, whereas the methyl orange is not. The next one is a titrating a strong acid with a weaker base. You can see the titration curve for HCl being a strong acid with ammonium hydroxide, which is a weak base. When ammonium hydroxide is added, the pH of the solution rises gradually. Around the equivalence point, a sharp rise in pH occurs approximately from the range of 3 to 8. We know that the pH range of methyl orange is 3.1 to 4.4 and that of methyl red is 4.4 to 6. Falls on this range and therefore the methyl orange and the methyl red are suitable indicators for titrating strong acid with a weak base. The last one is titrating a weak acid with a weak base. Here the titration curve for acetic acid, which is a weak acid, and with ammonium hydroxide, which is a weak base, is shown in this slide. The pH of this titration solution rises gradually and there is no sharp changes in pH around the equivalence point. Here the vertical portion is missing in the titration curve. Under these conditions, all the indicators changes color only gradually. Here there is no indicator is suitable for this type of titration. Thank you.